Hello everyone, this is Hamada Rizk, and today I'm going to share with you our paper, Ubiquitous and Accurate Floor Estimation System using Deep Representational Learning. And this is a joint work with Professor Hirizumi Yamaguchi and Professor Tiro Higashino and Professor Mustafa Yusuf. I will start with the motivation behind this work. 2D localization is most prevalent, raising the need for floor estimation. The floor estimation or vertical localization can limit the search space in multi-story buildings where fast response to emergency calls is crucial. Additionally, floor estimation can be integrated with 2D localization to provide 3D indoor navigation. There are several approaches proposed for floor localization and can be in general categorized into Wi-Fi based systems, which are widely adopted by utilizing the received signal strengths from the access points installed in the building. However, this requires high Wi-Fi coverage, which may not be available in every indoor environment. Additionally, instability is usually occurred by replacing and upgrading access points. This adds the cost of recalibrating the running systems. On the other hand, we have sensor-based systems, usually harness the onboard inertial sensors and or barometer of smartphones to track the user floor by employing bead reckoning. Nevertheless, these sensors are noisy, leading to an error accumulating over time. Additionally, all sensor-based systems require high-end phones to work, limiting their ubiquitous availability. We adopted cellular signals in this work as it is ubiquitous and widespread technology, and the cell towers are everywhere. Additionally, cellular signals are received by all cell phones, including low-end and high-end phones. The floor estimation system can work at the provider side or the client side with zero extra power consumption, in addition to the normal phone operation. The network has rare infrastructure changes due to the consequent expenses when doing this operation frequently. All these advantages, among others, suggest cellular signals as a promising ubiquitous solution for floor estimation. The basic idea is to use a fingerprinting technique which consists of an offline phase during which cellular signals or received signal strengths are recorded while the user is freely moving horizontally and vertically, annotating data by floor ID she is currently located in. Then this data is stored in a fingerprint database, which is then used to train a localization model for estimating the user floor in the online phase. However, using cellular signals for the floor estimation task faces some challenges, including handling the noise inherent in the wireless channel, handling the overlap in the original signal space between the vertical and the horizontal user motion, which hinders the discrimination of different floors. As in this figure, the X and Y axes are the RSS from two different cell towers, and each point is the RSS captured at a specific floor. As can be seen here, classification between different floors is not an easy task, even for efficient classifier. Finally, providing the required amount of data for the effective adoption of deep learning is challenging since it needs a lot of data collection. We propose CellRise, a deep learning-based system for floor estimation in multi-story buildings using ubiquitous cellular signals. CellRise provides a novel module to extract floor discriminative representation, characterizing different floors, given the overlap in the original signal space between the vertical and horizontal motion. These representations are then fed to a recurrent neural network that learns from the history or sequential changes in signals to estimate the user floor. Additionally, CellRise incorporates a module to process and generate artificial data to allow the effective application of deep learning. Finally, we deployed CellRise in two realistic indoor environments. This is our agenda for today, and I'm going now to describe the details of CellRise. The system architecture of CellRise consists of two stages, offline stage and online stage, including several modules to collect and process cellular data. Then floor discriminative features are extracted using the feature extractor module, which consists of deep LDA network. These features are then used for training a recurrent neural network, generating a localization model that can be used in the online stage for estimating the user current flow. The data collector module collects cellular signals at different floors of interest using collector application installed on the user's phone. The app scans for the cell tower here in the area of interest. Each scan represents cell information from up to 7 cell towers. This information includes the tower ID and its corresponding RSS. The data is labeled with the floor it is recorded in. The collected scans are then processed to extend their length from 7 towers or less to the length of all detectable towers in the area of interest across all scans. So in any scan, non-here towers are assigned RSS of 0. CellRise also employs data augmentation techniques to generate artificial samples. This provides the data required for training deep neural networks without extra data collection overhead. CellRise employs sampling technique, which samples from the RSS distribution of each cell tower. Also, generative models like variational autoencoder are adopted here. And finally, white Gaussian noise is added to the original RSS scan to generate new samples. Training the deep network with these artificial samples, in addition to the original data, boosts the system generalization ability. For more information, please visit our paper. The feature extractor module. The goal of this module is to obtain features in the latent space where different floors can be easily classified. Towards achieving this, we adopted deep linear discriminant analysis approach called deep LDA. Compared to the classical LDA, performs a linear mapping from the input to the latent space, deep LDA learns a more powerful nonlinear mapping and leading to a more separable latent space. The projected data in the new space can be seen here from these figures in two-dimensional space only for visualization. The figures show the improvement of the separation as compared to the raw RSS feature space. This is the network structure of the proposed deep LDA. The network consists of a number of cascaded fully connected layers with deep LDA layers stacked on top of the network. The output of the network is the intended latent representation Z, which corresponds to the floor discriminating feature vector. The loss function for the deep LDA network targets maximizing all eigenvalues of the output of the LDA layer. This maps to a projection that maximizes the separation between classes in the latent space. The model constructor. CellRise not only takes the current RSS scan into consideration, but a window of previous scans as well. A recurrent neural network, a stacked LSTM, is adopted in this module. The intuition behind using R in N is that the user cannot commute between different floors instantaneously. Additionally, recurrent neural network takes into account the change of the input features over time, leading to a better floor discrimination. This network is trained to operate as a multinomial classifier by leveraging a softmax activation function in the output. This leads to a probability distribution over the different floors of interest given an input. CellRise reports the weighted average of the reference floors, where their weights are chosen as their corresponding probabilities as the output from the classifier model. We further employ additional discretization operation to obtain the final user floor. This helps the system to provide an estimate for the user floor, including unseen floors. And also it helps us to collect the fingerprint at sparse floor, not all floors in the building. Now the evaluation section. We collected data in two different test beds in a mall of 10 floors and in a campus building of 5 floors, 5 users and 6 different Android phones. The feature extractor effect. This figure depicts that the proposed deep LDA method has superior performance compared to the raw features and the classical LDA and also the autoencoder. This can be explained by noting that the raw features are not highly floor discriminative. On the other hand, the classical LDA assumed that a linear transformation of the input improves separability in the new space, which is not always the case in practice. autoencoder network doesn't compete favorably with deep LDA as it is optimized for minimal reconstruction loss rather than class separability. These results confirm the efficacy of deep LDA in enabling accurate floor identification. Here we test the performance of CellRise in two different operators, and it obtains a consistent performance, as we can see from the figure. Here we compare CellRise to Skylock system, which is a state-of-the-art cellular-based floor localization system that uses key nearest neighbor to find the floor whose fingerprint is the most similar to the signal scan received at the online phase. CellRise outperforms Skylock in the two test beds due to it has a provision to extract floor discriminative features and also the power of using deep learning. Finally, this figure shows that CellRise has a significant reduced power consumption profile compared to GPS, Wi-Fi, and barometer, as cellular is enabled on the phone by default, so it adds no extra power consumption to the normal phone operation. Conclusion. In conclusion, we presented CellRise as a ubiquitous floor estimation system that utilizes feature extraction capability of deep LDA network. We showed how CellRise leverages a richer cellular information to build an accurate floor detection using recurrent neural network. We also showed how CellRise achieved a consistent high accuracy in different test beds and with different operators. Thank you so much.